last week we already talked about the internet, and we go for some video last week. And this week we'll continue to talk about the networking and go into more detailed stuff in here, okay, in the networking topic. So let's see. Last week we roughly dropped off right here. We actually finished some basic network idea, and then we haven't touched this one called the need for the IP address for the IP address packaging and protocol. Okay, we probably haven't go to here yet. This one, this battleship we haven't touched yet. Okay, so last week we are stuck here. So let's get started first. Okay, so last time we talked about network. Last time we talked about network. And we talk about 7-layer architecture, right? And we talk about the physical layer, they are wires, and level 1, the different media, okay? And we talk about top level, we had a browser, okay? Today we are more focused on the transport layer and the network layer right here. We'll be focused more on those different layers, okay? And we also talk about the difference between UDP and TCP, this portion, okay? This one, I think we covered it a little bit, okay, last time. Okay, so this portion is what we will get started. So this here we finish it, building the network, we finish. This time we get started from the need for the IP address, okay? The need for IP address. So basically, IP address is a number assigned to any item that's connected to the internet, okay? And this one is in the third layer. It's called IP layer, okay? Network layer. And the fourth layer is called transport layer. Okay, so transport layer is responsible for cutting your big chunk of data into packages and then send it out, okay? And we talked about protocol last time, okay? So this one you must remember, protocol is a set of rules governing the exchange or transmission of the data between the devices. So it's a set of rules, number one, actually, and also it is also to define the exchange and transmission of the data between the devices, okay? That's very important. And we will be focused on this level 3, level 4 stuff. Okay, level 3, level 4. So basically, your browser is HTTP is level 7, right? You hit the URL and hit return, you will send it. And then presentation layer would actually do encryption. Okay, so it actually will encode it and keep it a secret. Okay. And then you send to the session control. Session control, it actually control the time, control the security, okay? And then your video file may be big, okay? And you'll be cut into chunk in the transport layer. So each chunk of them actually, for example, original video file may be 1 gigabit, okay? And you cut into 1K bit or 1K byte as a packet, okay? And then you send to the network layer. And then from there, it's package by package. You send up and down to different router. So these different routers are intermediate points. So you send it from, say, San Francisco, go to Utah, okay? And then go to Chicago, for example, and then eventually go to New York, okay? So this middle router is here, okay? This middle router is only go up to the level 3 and then come down to, okay? And source is this from level 7 coming down to level 1, okay? And destination coming up from level 1 back to level 7, okay? So this is the basic idea that we have for the network. Okay, and today we more focus on the IP address. So IP address is an address that you need for any computer. I think last time we may already see some video on the IP address, okay? And then here there's a game, okay? This is a game called Battleship, okay? Battleship. So in the old day, we play game like this, right? We play some Battleship, the board game like this. And the other player have the same box like this, okay? So you basically put your battleship in certain location, right? In certain location, and you try to see which one hit, which one miss, okay? And then you put your hit as a red dot over here, okay? Miss as a white dot over there, okay? So basically, you play such a game. In the old days, something like this, okay? And if this one go to the internet, okay, go to internet, then it's different, okay? It's different. So when we have the internet version of such a game, basically they will be a server, okay? They will be a server. And then your player one is here, okay? Player one is here. Player two actually is here, okay? So server has a database of a game board, okay? And then initially your player's window will be set up somehow here, okay? And here you will also set up some game board. So player one need to register to the server. So you know that the player one's IP address is say 2.251.74.4, okay? And player two has another IP address. You need to register at the server, maybe 194.72.44 and 7, okay, whatever number. So two register on the server, okay? And then actually, you do not have the whole game board download to your local site. No, you do not need that, okay? And you do not update your information with the whole game board as well, okay? So initially, you set up your own game board, and he set up his own game board, okay? And then every time you make some changes, you upload the changes to the game board in register here, okay? And it will send the changes to your partner, okay? And your partner's change will also register on it and then send to here. So basically, it's only sending the transactions on the players to the server, okay? So that will minimize the transaction that needed for the whole system, okay? That will minimize the whole transaction. So that is something we need. But you do need to know about the IP address of the other player, and you keep that into a server. And this server, actually, sometimes we call it host, right? Sometimes we call it server, okay? So you know that people say it's a game server. Game server is, say you play a League of Legends and there's a game server. So game server is in charge of hosting the whole game, and then different players just register them and then exchange the information between server and the player. Okay, to make this happen, we need to have internet, right? We need to have IP address, and we also need to have a game rule. And then the game rule, IP address, and whatever, these are different kind of protocol at different level, okay? So that actually is a battleship game, okay? It's a battleship game. So this is a battleship game. This battleship game, you can search internet, okay? Search internet. So here we have battleship online game. So this is a battleship online game here. Let's see. Actually, let me see. It may have text mode, okay? We have text mode battleship game. Now let me show you the non-text mode first, okay? So here this one is a text battleship game. Okay, set up your battleship game. Whenever you update, okay, update your ship location. So this information will be sent to the server, okay? This information will be sent to a server. So I set up a game and it set up you will actually send to a server. So right now, the enemy is a computer. Okay, enemy is a computer. So the computer also is in the server, but sometimes the player may be remote different player, and you will register to the server as well. And right now, I send my information. So basically, you just need to send what location your ship occupy. Okay, and you will register on the map or on the server. So you keep sending the exchange file to me and the other player, or update the computer game. Okay, so that's what will happen. So something like that, right? So and then I start the sum already. Okay, so I may try to hit it. Okay, and you will update the game ball. Okay, so I update my location. So far, I did not hit this ship. Okay, so far I did not hit this ship. So far, actually, okay, right here I hit a ship. Okay, I hit a ship location. So right here there is a ship got hit, and this green one actually is a miss. Okay, so I continue to hit its nearby. Okay, so right there there's no ship. So apparently this ship maybe is it's actually horizontal. So I keep hitting, so I hit another ship. So something like that, okay, something like that. So basically this game, you will need to transmit some information back and forth between the players, okay? And that require the IP address and also the transportation of the data in order to make it work, okay? So first thing is the domain name translation, okay? So let's look at one video for the domain name translation, okay? Let's see, sorry, one moment, okay. So last time okay, by physical layer. I think last time the cable wire, we finished it, okay. So today, I don't know whether this one we play or not, but if we do play already, so let me know, okay. So this one is the first one, let's look at the IP address, okay.
My name is Paula, and I am a software engineer at Microsoft. Let's talk about how the internet works. My job relies on networks being able to talk with one another. But back in the 1970s, there was no standard method for this. It took the work of Vint Cerf and Bob Kahn to invent the Internet Working Protocol to make communication possible. This invention laid the ground.
Okay, so these two people are involved in the first interneting protocol, and the ARPANET, we talked about it last time already, okay? And today we are talking about a detailed IP protocol. This IP protocol, what they are talking about is in the layer 3, okay? In the layer 3, the networking layer, in actually exchanging, the networking layer is in charge of the address and sending the data to the remote side, okay, through the routers.
Work for what we now call the internet.
The internet is a network of networks. It links billions of devices together all around the globe. So maybe you're connected with a laptop or a phone through Wi-Fi, but then that Wi-Fi connection connects to an internet service provider or ISP, and that ISP connects you to billions and billions of devices around the world.
Okay, so the ISP actually is your AT&T or Verizon, okay? So your own laptop connected to your router at home, okay? Your router at home through Wi-Fi. Or you go to McDonald's, and McDonald's has its own Wi-Fi. So here it actually using the wireless connected to there. And then they must have a router and modem, okay? They must have a modem, and the modem connected to ISP, okay? So ISP is say AT&T, or maybe Verizon, or maybe Comcast, whoever provides internet service for you. And then starting from there, it connected to the internet, okay? Starting from there, it connected to the internet. If your device is a cell phone, it connected to the base station, okay? And keep When you keep moving, it's actually being connected to different base station. Okay, it is registered to different station, and then if you go between boundary, the control of the cell phone will be transferred to the next base station, and then the base station connected to internet. Okay, something like that. Okay, so that actually in different network, using different way to connect your device. Okay, so here talking about from ISP get out to the internet. Okay.
Through hundreds of thousands of networks that are all interconnected. One thing that most people do not appreciate is that the internet is really a design philosophy and an architecture expressed in a set of protocols. A protocol is a well-known set of rules and standards that, if all parties agree to use it, will allow them to communicate without trouble. How the internet actually physically works is less important than the fact that this design philosophy has allowed the internet to adapt and absorb new communication technologies. This is because in order for a new technology to use the internet in some fashion, it just needs to know which protocols to work with. All the different devices on the internet have unique addresses. An address on the internet is just a number, similar to a phone number or a sort of street address that's unique to each computer or device at the edge of the network. This is similar to how most homes and businesses have a mailing address. You don't need to know a person to send them a letter in the mail, but you do need to know their address and how to write the address properly so the letter can be carried by the mail system to its destination. The addressing system for computers on the internet is similar, and it forms part of one of the most important protocols used in internet communication, simply called the Internet Protocol, or IP. A computer's address then is called its IP address. Visiting a website is really just your computer asking another computer for information. Your computer sends a message to the other computer's IP address, and it also sends along its origin address so the other computer knows where to send its response.
You may have seen an IP address. It's just a bunch of numbers. These numbers are organized in a hierarchy. Just like a home address has a country, a city, a street, and a house number, an IP address has many parts. Just like all digital data, each of these numbers is represented in bits.
Okay, so basically the IP address, the one you are seeing right now is called IPv4, okay, version 4 IP address. So version 4 IP address actually is a 4-byte, okay, 4-byte. 32 bits. Okay, so each one of them is 1 byte, 1 byte, 1 byte, 1 byte. 1 byte is 0 to 255. Okay, 1 byte is 0 to 255. So the number always is 0 to 255. Okay, for 4 numbers, and this is called IP address. Okay, this is called IP address, and this is IPv4. And later we will talk about different version, but this one is the initial version, is like this. Okay.
IP addresses are 32 bits long, with 8 bits for each part of the address. The earlier numbers usually identify the country and regional network of the device. Then come the subnetworks, and then finally the address of the specific device. Okay, so this chart is very important, okay? So the 4 number, the first number is called country on a network, okay? So country may be .US, okay? Maybe .cn for China, okay, something like that, okay? And then network may be .edu or something, that's a different network, okay? And then region may be, say, California or whatever, that's a region. And then right here is a network and then device, okay? So these two are more public, global, and these are local, okay, they're local. So basically, some network usually is your own building, maybe it's one subnetwork, and then the whole devices in the LAN is called hooking up with these devices. Okay, so these are 4 different levels. But right now, this system already been jammed, not enough address space already. But in the old days, this is the standard that people use. This version of IP addressing is called IPv4. It was designed in 1973 and widely adopted in the early 80s. and provides for more than 4 billion unique addresses for devices connecting to the internet. But the internet has turned out to be much more popular than even Ben Cerf imagined. And 4 billion unique addresses won't be enough. We're now in the middle of a multi-year transition to a longer IP address format called IPv6, which uses 128 bits per address and provides over 340 undecillion unique addresses. That's more than enough for every grain of sand on Earth to have its own IP address.
Most users never see or care about internet addresses. A system called the Domain Name System, or DNS, associates names like www.example.com with the corresponding addresses. Your computer uses the DNS to look up domain names and get the associated IP address, which is used to connect your computer to the destination on the internet.
And it goes a little something like this.
Hey, hi there. I want to go to www.code.org.
Yeah, I don't know the IP address for that domain. Let me ask around. Hey, they know how to get to code.org?
Yeah, I got it right here. It's 174.129.14.120.
Oh, okay, great, thanks.
Okay, so so basically your computer have the request of what is www.code.org, right? You have the such request. You don't know the IP address for it. So the one he actually asked for is the ISP, your AT&T or your Comcast server, right? And he doesn't know as well. He doesn't know as well, then he requests for DNS, okay? So later this portion, we will have a separate video to look at it, okay? But basically, it has to ask for different domain name server. But domain name server is not one computer. It's actually is the whole internet is a domain name server. So domain name server is distributed, it's actually everywhere, and it is all over the world, okay, all over the world to provide a service. So it's a distributed system, okay, it actually is a distributed system. So to maintain this, we have different protocols. So later we'll show you, but basically you send out the request to the address, the name, I'm sorry, you then send out the name and then translate to some IP address, okay. So this one, domain name service, you try to get a domain name. It is a translation from a website to a number, to an IP address, okay, to an IP address. And IP address is two versions, IPv4, that actually is 32 bits, okay, we talk about it, it's actually 4 bytes. And then newer version is IPv6, that's 128 bits. It's actually 7 bytes, okay. So the newest system actually has 3 more bytes, okay, 3 more bytes. And actually right now, people are upgrading the IPv4 to IPv6, okay, and continue, okay.
Yeah, I'm gonna write that down and save it for later in case I need it. Hey, here's that address you want.
Awesome, thank you.
So how do we design a system for billions of devices to find any one of billions of different websites? There is no way one DNS server can handle all the requests from all devices. The answer is that DNS servers are connected in a distributed hierarchy and are divided into zones, splitting up responsibility for the major domains, such as .org, .com, .net, etc. DNS was originally created to be an open and public communication protocol for government and educational institutions. Because of its openness, DNS is susceptible to cyber attacks. An example attack is Dns spoofing. That's when a hacker taps into a DNS server and changes it to match a domain name with the wrong IP address. Okay, to actually modify the IP address, this actually hacking is called DNS spoofing. Okay, spoofing. So this term you must remember. Okay, if the test asks you what kind of the
hacking or problem it is. You have to remember this word is called DNS spoofing. So it's possible that certain hacker may go to some domain name server and then change your IP address. So code.org may not be able to deliver the data to you because their IP address already been rerouted to different location. Okay, rerouted to different location.
This lets the attacker send people to an imposter website. If this happens to you, you are vulnerable for more problems because you are using that fake website as if it is real. The internet is huge and getting bigger every day, but the domain name system and internet protocol are designed to scale, no matter how much the internet grows.
Okay, this message is very important. What she said is that the internet is designed to scale. It means that you add in more devices at any time. Say here at your home, you have one laptop and you connect another and yet another. Okay, at any time, actually, as long as your router allow, it can all communicate through the internet, right? And internet is a certain server, and there may be some cell phone going to certain base station. Some car just drive by, and then the new cell phone hook up with the base station. So the number of the devices keep moving and keep adding more devices to the network, but they all be able to add on to the internet. That's because that our internet is designed to scale. It's scalable. Okay, it can grow at any time. And the only problem right now is that the IP address is limited. So we work on a newer version of the IP address in order to accommodate all the devices. Otherwise, the current infrastructure is designed to be scalable, and also it's also distributed. So the whole system is actually spread over everywhere. Okay, spread over here is distributed. Okay, it's called distributed. Okay, this one is a good video from code.org. Okay, so anyway, let's go back to the game that we talk about. Okay, let's go back to the game that we talk about. So here you do have a player. Okay, and he see his own game, but there's a server. Okay, so the server actually has also set out a database. Okay, so here is a server, and then the player 2 is over here. Okay, player 2 is over here. Player 1 is over here. So every time you just send your transaction, so I hit here, okay, and he will report. Okay, this one actually is a miss. For example, it's actually a miss. Okay, whatever, and then he will actually also report that he hit here, and I will actually report it's a hit. So whatever. Okay. So this one actually, player 1 would need to register its own IP address. That's as soon as 1.1.1.1. Player 2 is 2.2.2.2. Okay. So here we do have a server. So in the old day, actually people call it cloud computing. Okay. And cloud computing had a server on it. Okay. Have a server on it. So this one is actually called cloud computing. So server is there, and this model. Actually server, okay, and client computing model have been there for quite a while, okay, and recently this model been expanded, okay, so people don't like this idea, so no more server, okay, no more server, okay, no more server. People don't like the so-called centralized system. So this the system that we talk about so far with a server that's called centralized system. Okay, so right now they like the other word called distributed. Okay, distributed system. So basically, that's the so-called meta universe come in. Okay. Okay, so the server may not be only one computer. It actually is a lot of server in the internet, right? and then you hook up to a certain server, okay, and he will hook up through his local server somewhere. But these two people is able to play game and in a distributed environment. So this one is called a meta universe, or maybe called a Web 3.0. So these are the new terms. This is just come in recent 2 years, okay, just come in recent 2 years. So we are actually in the age to converting from centralized system to distributed system right now, okay? So the server right now is actually still undergoing a big construction of coming from centralized to distributed, okay? And this one, the whole environment right now still under change, okay, still under change. And that is the beginning point of the internet, okay? So second one, that would actually, let's look at how IP address work, okay? So let's look at another video. This one is how domain name server work, okay? How domain name server work. So let's actually look at this one, how domain name.
In the world of networking, computers don't go by names like humans do. They go by numbers, because that's how computers and other similar devices talk and identify with each other over a network, which is by using numbers such as IP addresses. Humans, on the other hand, are accustomed to using names instead of numbers. Whether it's talking directly to another person or identifying a country, place, or thing, humans identify with names instead of numbers. So in order to bridge the communication gap between computers and humans and make the communication a lot easier, networking engineers developed DNS. And DNS stands for Domain Name System.
Okay, so domain name systems, the main idea is, the main idea of domain name system is, let's clear this one, okay? So whenever you have the address bar, right? And you type in www.example.com, okay? So this one actually is layer 7, okay? So you hit return. So the URL being sent to the browser. Browser engine try to find the IP address. So the translation scheme that we have trying to find the IP address. Eventually, you need to identify the IP address. Okay, so identify the IP address. So the process of coming from the domain name, this one we call it domain name. This is domain name. This is subdomain. Okay, so domain name, from the translation from the domain name to IP address, this whole thing is called domain name service. Okay, sometimes it's called domain name service, sometimes called domain name system. System means the hardware, okay? Hardware and system. Server means that there are some computer helping you to solve the problem to get IP address. So this whole process is called domain name service, okay? And the video you're about to watch is relating how the translation being done, okay? How the translation being done. So this translation is done, and your level 7 find the IP address. So he know that where is the destination. So the destination may be code.org, okay? So you will use the IP address of the source location to the destination location. But in the middle, you still need to find the IP address for the router in the middle, okay? You still need that. You still need to do that. So the whole domain name system is very important, okay? It's very important. Let's go back to the video. So now this is the domain name system that we use to do translation, okay?
And DNS resolves names to numbers. To be more specific, it resolves domain names to IP addresses. So if you type in a web address in your web browser, DNS will resolve the name to a number, because the only thing computers know are numbers. So for example, if you wanted to go to a certain website, you would open up your web browser and type in the domain name of that website. So for example, let's use yahoo.com. Now, technically, you really don't have to type in yahoo.com to retrieve the Yahoo web page. You can just type in the IP address instead if you already knew what the IP address was. But since we are not accustomed to memorizing and dealing with numbers, especially when there are millions of websites on the internet, we can just type in the domain name instead. and let DNS convert it to an IP address for us. So back to our example, when you type in yahoo.com in your web browser, the DNS server will search through its database to find a matching IP address for that domain name. And when it finds it, it will resolve that.
Okay, so number one, the IP address, actually, if you do know your IP address, you can directly type in here. Okay, so I can do 127.0.0.1. Okay, so 127.0.0.1. Okay, you will see something like this. Okay, it's called Internet Service Windows. Who is this guy? 127.0.0.com is called localhost. Okay, so the computer I'm using right now has a local server. Okay, it's called 127.0.0.1. Okay, that's called localhost. So it's wherever is connected to my own computer. But technically, you can just type in the IP address and you should be able to find it. Okay, you should be able to find which actual computer it is. So you can also do the IP address for Google. Okay, so IP address for Google, there are some IP address you can find. Okay, whatever you can actually find a IP address for it, and technically you type in on the address bar, you should be able to find. And usually you have the 192.168.0.1, for example. So 196.0.1 or maybe 192.168.0.0. Okay, this location usually the two number we have 192.168.something. These are reserved for your local area network. So actually it's inside your router. Inside your router is this number, okay? But I have to guess a little bit to find out my router's location in my home, okay? It's usually some number in 192.168.0.1.2.3.4. Some of them I should be able to find my router. I can look at the user menu, but right now I cannot find it, okay? But these are some fixed addresses that you can find. Those are some fixed addresses that you can find, okay? Okay, so let's see. Okay, so this one is the address, okay? Where's the video? Where's the video? Okay, one moment. Wait, I may have lost my video link. Right here, this one. Okay, sorry. Okay, sorry. It's this one. Cool.
Domain name to the IP address of the Yahoo website. And once that is done, then your computer is able to communicate with the Yahoo web server and retrieve the web page.
Okay, so basically Yahoo address after translation may be something like this. So in principle, you can just use this number, put on your IP address bar, and you will find a Yahoo server, okay? But usually people cannot remember this. So you need to use a domain name.
So DNS basically works like a phone book. When you want to find a number, you don't look up the number first. You look up the name first, then it will give you the number. So to break this down into further detail, let's examine the steps that DNS takes. So when you type in yahoo.com in your web browser, and if your web browser or operating system can't find the IP address in its own cache memory, it will send the query to the next level to what?
Okay, so number one, when you actually trying to use your browser, say Google Chrome, and you type in yahoo.com, right? So for example, and then the first one you check is the cache memory. So cache memory is inside your browser. So inside your browser, you already look at whatever you already browsed so far. So maybe YouTube's location, it has some IP address, okay? Maybe Wall Street Journal.com, okay, whatever it is, some IP address. So these are some you frequently browse website, it already store in the cache. But maybe this Yahoo.com is in there, maybe not. If not, then you cannot get the address right away. If yes, you already get the address, then that's done. Okay, that's done. So domain name service is not only one computer. It's starting from your own browser, okay? And it's a whole system. So the whole system is not one computer. It's not always on the internet. It may be only in your own computer, maybe in the ISP, maybe in other computer. It's actually the whole system. So the first one, you check your browser, and your browser doesn't have, then you will go to a resolver. And this resolver, the first one you will look at is ISP, is your AT&T office, okay? That's the second one you would look for, okay? And you will send the request to the resolver, okay?
What is called the resolver server. The resolver server is basically your ISP or internet service provider. So when the resolver receives the query, it will check its own cache memory to find an IP address for yahoo.com. And if it can't find it, it will send the query to the next level, which is the root server.
Okay, so now AT&T trying to look at its own cache as well. Okay, and it actually had bigger memory than your computer, so you will check there. And usually 99% of the address I think is over there. Okay, so something like Facebook.com, Yahoo.com, I think that's no brainer. Usually your own browser or resolver should have it. Okay, only very few websites that actually you need to go to the next level. The next level will go to the root server. And root server is where there are 13 different root server. It's a service for .com, okay, .edu, okay, say .big, okay, .net, okay. This kind of the root server, there are 13 of them. There are only very few of them, and that's called root server, okay, that's a domain root server.
The root servers are the top or the root of a DNS hierarchy. There are 13 sets of these root servers, and they are strategically placed around the world, and they are operated by 12 different organizations. And each set of these root servers has their own unique IP address. So when the root server receives the query for the IP address for yahoo.com, the root server is not going to know what the IP address is. But the root server does know where to send the resolver to help it find the IP address. So the root server will direct the resolver to the TLD or top level domain server for the .com domain. So the resolver will now ask the TLD server for the IP address for yahoo.com. The top level domain server stores the address information for top level domains, such as .com, .net, .org, and so on. This particular TLD server manages the .com domain, which yahoo.com is a part of. So when a TLD server receives the query for the IP address for yahoo.com, the TLD server is not going to know what the IP address is for yahoo.com. So the TLD will direct the resolver to the next and final level, which are the authoritative name servers. So once again, the resolver will now ask the authoritative name server for the IP address for yahoo.com. The authoritative name server or servers are responsible for knowing everything about the domain, which includes the IP address. They are the final authority. So when the authoritative name server receives the query from the resolver, the name server will respond with the IP address for yahoo.com.
Okay, so basically, the resolver don't have it. It check the root server and then top level domain server, and then to the authoritative name server. So these are, he just asks for other people for it. Okay, anyway, this one is the process of finding the IP address. Okay, so after you find the IP address and you start to know about which one you will send the data to. Okay, you will send the data to. Then the package will start to travel. Okay, the package will start to travel. So next one, let's see. Okay, let's see. Actually, okay. So next one, let's look at the internet, the router and package. Okay. So let's look at the level 4.
6, 5, 4, 3, 2, 1.
Hi, my name is Lynn Root. I am a software engineer here at Spotify, and I'll be the first to admit that I often take for granted the reliability of the internet. The sheer amount of information zooming around the internet is astonishing. How is it possible for every piece of data to be delivered to you reliably? Say you want to play a song from Spotify. It seems like your computer connects directly to Spotify's servers, and Spotify sends you a song on a direct, dedicated line. But actually, that's not how the internet works. If the internet were made of direct, dedicated connections, it would be impossible to keep things working as millions of users join, especially since there's no guarantee that every wire and computer is working all the time. Instead, data travels on the internet in a much less direct fashion.
Many, many years ago, in the early 1970s, my partner Bob Kahn and I began working on the design of what we now call the internet. Bob and I had the responsibility and the opportunity to design the internet's protocols and its architecture. So we persisted in participating in the internet's growth and evolution for all of this time up to and including the present. The way information gets transferred from one computer to another is pretty interesting. It need not follow a fixed path. In fact, your path may change in the midst of a computer-to-computer conversation. Information on the internet goes from one computer to another in what we call a packet of information. And a packet travels from one place to another on the internet, a lot like how you might get from one place to another in a car. Depending on traffic congestion or road conditions, you might choose or be forced to take a different route to get to the same place each time you travel. And just as you can transport all sorts of stuff inside a car, many kinds of digital information can be sent with IP packets, but there are some limits. What if, for example, you need to move a space shuttle from where it was built to where it will be launched? The shuttle won't fit in one truck, so it needs to be broken down into pieces, transported using a fleet of trucks. They could all take different routes and might get to the destination at different times. But once all the pieces are there, you can reassemble the pieces into the complete shuttle and it'll be ready for launch. On the internet, the details work similarly. If you have a very large image that you want to send to a friend or upload to a website, that image might be made up of tens of millions of bits or ones and zeros, too many to send along in one packet. Since it's data on a computer, the computer sending the image can quickly break it into hundreds or even thousands of smaller parts called packets. Unlike cars or trucks, these packets don't have drivers and they don't choose their route. Each packet has the internet address of where it came from and where it's going. Special computers on the internet called routers act like traffic managers to keep the packets moving through the networks smoothly. If one route is congested, individual packets may travel different routes through the internet, and they may arrive at the destination at slightly different times or even out of order.
So let's talk about how this works. As part of the internet protocol, every router keeps track of multiple paths for sending packets, and it chooses the cheapest available path for each piece of data based on destination IP address for the packet. Cheapest in this case doesn't mean cost, but time and non-technical factors such as politics and relationships between companies. Often the best route for data to travel isn't necessarily the most direct. Having options for paths makes the network fault tolerant, which means the network can keep sending packets even if something goes horribly, horribly wrong. This is the basis for a key principle of the internet, reliability. Now, what if you want to request some data and not everything is delivered? Say you want to listen to a song. How can you be 100% sure all the data will be delivered so the song plays perfectly? Introducing your new best friend, TCP, Transmission Control Protocol. TCP manages.
Okay, this one TCP is the layer 4 protocol. Okay, so not one layer above the IP address. Okay, so combined we call it TCP/IP, but sometimes the layer 4 may use UDP. Okay, that's another story we'll talk about later. But the one that cut the big chunk of data from from a big file to a smaller chunk of of the package is called using the TCP, okay, transmission control protocol. Okay, we'll discuss this later after video, okay.
Manages the sending and receiving of all your data as packets. Think of it like a guaranteed mail service. When you request a song on your device, Spotify sends a song broken up into many packets. When your packets arrive, TCP does a full inventory and sends back acknowledgements of each packet received. If all packets are there, TCP signs for your delivery and you're done. If TCP finds some packets are missing, it won't sign. Otherwise, your song wouldn't sound as good, or portions of the song could be missing. For each missing or incomplete packet, Spotify will resend them. Once TCP verifies the delivery of many packets for that one song request, your song will start to play. What's great about the TCP and router systems is they're scalable. They can work with 8 devices or 8 billion devices. In fact, because of these principles of fault tolerance and redundancy, the more routers we add, the more reliable the internet becomes. What's also great is we can grow and scale the internet without interrupting service for anybody using it.
The internet is made of hundreds of thousands of networks and billions of computers and devices connected physically. These different systems that make up the internet connect to each other, communicate with each other, and work together because of agreed upon standards for how data is sent around on the internet. Computing devices or routers along the internet help all the packets make their way to the destination where they're reassembled if necessary in order. This happens billions of times a day, whether you and others are sending an email, visiting a web page, doing a video chat, using a mobile app, or when sensors or devices on the internet talk to each other.
Okay. So this video gives us the idea of how the transmission being done, okay? So let's actually look at this one in another way. Let's go back to our internet 7-layer architecture, okay? So I'm a user, okay? I'm using my Google Chrome, okay? So that's my label 7. And I'm trying to request some video from YouTube, okay? YouTube. So YouTube actually is my destination. So basically, number one, first things that I type in my address. So then there's a domain name server trying to help me. So it will come, give me some numbers. So I will know that my destination may be youtube.com, maybe. Let's assume that it's actually 4.4.4.4, okay? So that's my destination, okay? That's my destination. So here, okay, first I need to send my request down to the level 1, okay, go everywhere and come here. And then YouTube knowing about which video I'm going to download, okay? So at that time, YouTube already know that what kind of video will be downloaded. So let's assume that here, it has a big video. Say I would like to look at the football game, okay, that we recorded 3 years ago, okay? So that football game may be, say, 3 gigabyte, okay? And actually it take 2 hours or 3 hours to watch it. Let's assume it's 2 hours, okay? So basically it doesn't work that way that you download the whole 2-hour video back to my browser and then I can use my YouTube browser version to look at it, okay? It doesn't work that way, okay? This cannot be that way. So that's not going to happen in this way. So for YouTube to download it, okay, number one, it will send down its data, encrypt it, and then have some encryption, and also set up the session control, okay? And this 3 gigabyte, it will be actually breaking down into certain packages, okay, certain package. So each package actually has some numbers. So you have a 0, 1, 2, 3, whatever, okay? There's a timestamp or number being assigned to each package. So this package is being sent out one by one, okay? But when it arrives, it will not be from 0, 1, 2, 3, 4 in the order of the package number. It may arrive like 1 and then 10 and then 15 and then 2 and then 0, whatever. It may be out of order. But it's out of order than what my Google browser trying to assemble them. So it will actually keep, okay, 1, 2, 3, 4, 5, 7, 6, 3, 4, 5, 6, 7. Okay, this is enough. I back up for say 2 minutes. Okay, so that's my buffer. That's my buffer. I buffer enough of the video. Then I start to play my video on YouTube. So you do see like when we play video, okay, you do see that when we play video, I'm sorry. Okay, whenever we play some video.
And finally, the
okay,
result.
let's see. I'm sorry. When we play some video, here you actually usually have the red one, that's play bar. Okay, and there may be some tiny or big gray area that's called buffering zone. Okay, so it also shows you how much you have buffer. Okay, and this portion is unreached portion. So basically, red one you already played. Gray one actually is something that you haven't played but in buffer. Okay, how much buffering you have. But if your buffer and the play point is the same, then you don't have buffer. Then the video may be stuck for a while to buffer in again until you have all the video package arrive. Okay, so that buffering is also in your browser. You will do buffering. So buffering is there. Okay, and then you break into chunk of the data, and then they may arrive in different order. So that actually may have some out of order transmission. Okay, that's one thing. Second thing is like, okay, this one is actually about buffering and actually reassemble of the data. Second is like, okay, my from Yahoo to my home. Okay, so it will not go from Yahoo server. That's assume that this Yahoo server is in New York again. Okay, and my browser is in California, in San Francisco. So it will not go directly from New York to California. No stop, non-stop flight. It's not non-stop flight. It's not airplane that has a non-stop flight. Instead, in between the two city or two location, there are tons of different routers in the middle. Okay, and they kind of been built in such a network. Okay. So there are so many things there. Okay, it's been built up in a certain way. Okay, so it's okay. So basically there are tons of different points. Okay. So number one, actually, you start to they start to send the first package. So the first package may go this way. Okay, may go this way to arrive. Second package may go the other way. May go this way to arrive. Okay. Third package it may go this way. Whatever, they may not have the same way, and usually they don't. Okay, usually they don't. They just send out a different route. Okay, different location. Okay, so the number one, you never know which way it will go. So basically, what we know is that okay, in the package, you will actually write like okay, for example, my IP address is 2.2.2.2. So you will actually say that destination is 2.2.2.2. Okay, source is 4.4.4.4. Okay, and you send to the destination, and you forward your package from your source to one router. So from source to one router, it go from level 7. Go up to level 3, that's IP address level. And then IP address level of router of this one, he will determine whether you should go this way or go this way. Okay, he will determine whether you go this way or this way. It will depend on the traffic condition, how jammed this two route is, and it will determine. And then when it determines, it's forward to the next location. That's the that you pick this one. You'll go down to level 1 and send out. And then at this second router, you go up to the level 3 again. And you will actually, at that time, you will actually determine where you should go again. At that time, you will determine where you should go again. Maybe he pick a route here, okay? And then you go down to level 1 to transmit out, okay? So something like that. That the chart of level 3 back to 1, up to 3 back to 1 is something like this, okay? Each router determines which the next level, next point that it should send the data to, okay? Which point it need to send data to. So now here comes a problem, okay? Here comes a problem. So how about, okay, this is the network. Okay, let me actually clean it up. Okay, let's clean it up. Okay, so let's clean it up. Okay, so let's assume that actually here, okay. Okay, let's assume that somehow this one is dead. Okay, this one is dead. Somehow this one is dead, and then I transmit my data actually to here, to here. Okay, originally it's planning to go this way, right? This one is dead. But because of there are multiple paths, so you can actually instead send the data this way or this way. Okay, so you can bypass it. This one is the so-called fault tolerant. Okay, fault tolerant computing. Okay, so fault tolerant computing, this is one example. Okay, you provide multiple paths or redundancy to avoid the problem. Okay, and you will go different route and arrive. That's first fault tolerant. First fault tolerant is actually called hardware redundancy. Okay, hardware redundancy. So you actually provide multiple paths or multiple routes, then you can bypass a certain one, and then you can arrive at a destination. That's called hardware redundancy. Okay, so hardware redundancy, you can bypass it. That's the first way. Second is actually called software redundancy. Software redundancy means that, okay, my browser keep waiting for certain packages. Let's assume that package 1, 2, 3 arrive. Okay, number 4 that I arrive. Okay, number 5 arrived already. So basically, I have a buffer on my destination, have a package number 1, 2, 3, and then number 4 is missing, and I have 5, 6. So I have been waiting for 3 minutes, and I still don't see my number 4 coming. And it's too long. It's too long. It's already too long. So what happened is like, okay, in this way, at a certain time, my TCP may, okay, at the TCP level, okay, my TCP protocol may determine, I don't want to continue to wait. So you send back a request back to the server saying that, okay, your package 4 is missing. Then you do retransmit. So when the data being retransmitted back to the server, we call it a software redundancy. Okay, software redundancy. Software redundancy. So software redundancy means that we do retransmit. So retransmit will slow down the network. Okay, slow down the transmission. But you have to do that because you cannot afford the package to be lost. Okay, that's called second redundancy. So you have hardware redundancy, that's you build multiple paths to allow the data to go through, okay? And then you may have the software redundancy. There are third way of the redundancy, okay? So redundancy, you have first one that's a hardware. Hardware redundancy means that you provide multiple paths, okay? Provide multiple paths. Multiple paths, multiple computer, okay? Multiple router, we call it hardware redundancy. Second one is actually called software redundancy. So software redundancy is to retransmit. You retransmit your data. Third one is called information redundancy. So information redundancy means that in the data, you put the data over here, right? You put the data over here, but you do put some error correction code. Okay, error correction code. You put those error correction code over there. Okay, and then those error correction code arrive. This whole thing arrive at your destination, and the destination checking your error correction code and the data, see whether they match or not. If they don't match, then it will actually request the sender to reset as well. That means that the package has been destroyed in the middle of the transmission. For what reason, we don't know, but please retransmit. Okay. But in order to make sure that your data is safely arrived, you need to add extra error correction code. Now we call it information redundancy. So 3 redundancy. Okay. Keep this in mind. This is very important. Number 1, hardware redundancy. You provide multiple paths to allow the software to travel. Allow the data to travel the packages to travel through the internet. Okay, the multiple subpaths, multiple router, we call it hardware redundancy. Second one is the software redundancy. Software redundancy means that if it time out, you want the server to retrace me. Okay. Third one is the information redundancy. That means that your data put more error correction code into your thread and send. And at the your receiving side, you receive it and decode it. If it doesn't match, then means that the data may have been destroyed in the middle. So you also request a retracement. Okay. So these are three redundancy in the internet. Okay. These are the three redundancy that will happen in the internet. Okay. Okay, that actually is layer 4. Okay, that actually is a layer 4 TCP. Okay, so now let's actually look at another video that's related to TCP and the UDP. Okay, UDP and TCP both are the layer 4 standard. Okay, this one will be tested. Okay, very important topic. Okay, so now we look into the layer 3 and layer 4. Okay. Layer 4 is the transport layer responsible to cut the big chunk of the data into smaller packages. Okay. Layer 3 is responsible for forwarding the data from one computer to the next router. Okay. So that's a level 3. You always go up to level 3 only. Okay. In the layer 4, you already put them back to a big file already. Okay. You already did that. Okay. That's one thing. Okay. And then in the layer 4, there are two protocols being used. Okay, commonly used protocol. There are two being used. One is called UDP. The other one is called TCP. Okay, so this one more important. So let's look at this one. Okay.
We've talked about the OSI and TCP IP models. Now we're going to focus on two of the protocols in the transport layer. These are TCP and UDP. We're going to see how they get information from one application to another and their different approaches to their job. Two devices on a network rely on IP to deliver information between each other. This happens at layer 3, which may include routing packets across several networks.
Okay, before we get started. Okay, so basically your level 7, that's the Yahoo websites over here. There's some video you don't want to trust me. You want to trust me. Okay, so it actually being encoded, compressed, whatever. Go down to the TCP. So the TCP, it receives some data and it cut into smaller chunk of the packaging. So now they actually put into smaller chunks. So that's this smaller chunk is the data. Okay, it's the data. Then you are going to put some TCP or UDP header to it. Okay, in order to tell your destination what type of the transport layer protocol is being used. Then you put on the IP layer package, including the IP address onto it. And then you will look into, you will make data link layer. This one is layer 2 data. And you put the whole thing, this whole thing, we call it a data frame. Okay, data frame. It's in the layer 2. Okay. And you should using your MAC address to send the data. Okay, that's layer 2. But the whole data being packaged in this way. Okay. Being packaged in this way to be sent. So that actually every layer you add more data into it. Okay, in every layer you add more data into it. Okay, in every layer you add more data into it. So the whole going down from layer 7 to layer 1. Okay, it actually has a process of from data, putting your header and then adding your IP address, and then actually putting your frame, footer, and header. So it's a case called encapsulation. Your data being put more different protocols, extra information to there. Typically in layer 4, layer 3, layer 2. Okay, and layer 1 it already been converted to physical signal to send out. Okay, so it's something like that. Okay, so these are actually the encapsulation. So now let's go back to layer 4. Okay, go back to layer 4. So layer 4 actually is using two protocols. One is TCP, the other one is UDP. Okay, these two protocols are different. They are responsible for different way of transmitting data.
At layer 4, though, we see very different behavior. The transport layer doesn't care too much about the networks in between. Why? It doesn't need to. That's layer 3's job. It also doesn't care too much about the devices themselves. Instead, it cares more about getting data between applications. The two protocols that are responsible for this are TCP and UDP. They share a few things in common. For example, they both have headers and they both have port numbers.
Okay, so TCP's header are more data. Okay, TCP is called transmission control protocol. UDP is a uniform datagram protocol. So these two are two different protocols, and their header are different. Okay, and they have different source port, destination port, sequence number. Okay, they have different number checksum, and these two data frame and protocol determine how the data being handled and being transmitted. So the safety needs and also the security and the efficiency are different, okay, because of these two different protocols.
But as you can see in the headers, there's a lot more going on with TCP than UDP. That's because TCP supports a lot of features, while UDP is extremely lightweight. Through the rest of this video, we're going to see how TCP and UDP have different approaches to getting the job done, and why some applications will use one protocol or the other. In the header, you'll see fields for the source and destination ports. The ports are used to identify the applications on each device. In this way, ports are like addresses for applications. This is similar to how the devices themselves have IP addresses. When an application starts a conversation, it chooses a protocol to use as well as a random source port. This is some value from 1024 to 65,535. The exact number is generally not so important. The important part is that this port number is not already in use on the device. One port number cannot be given to more than one process at a time. The destination port number, that is the port number of the server application, is usually a well-known value. For example, if we were using HTTP for web browsing, the port will normally be port 80. Well-known ports are in the 0 to 1023 range. By making a port well-known, it's easy for the client to guess what port the destination application will use. If you want to see some well-known ports, have a look at the list in this URL. Of course, a server application could be configured to use a non-standard port, maybe port 81 for HTTP, for example. And this is fine, but the client can't guess the port number anymore. The client application will need to be manually configured to support this.
Okay, so one thing, okay, let me take it back a little bit, okay? So here, what's important is that there's a port number, that's the port number it talk about here, okay? So your IP address, and then there's a port number. Port number determine which buffer you use to take the data back, okay? And is actually need to be determined by the TCP to send the data. And then the port number will assemble the package back to your file, okay? Will assemble the data back to the file.
And there are different approaches to this too.
Okay, sorry.
How does it know which application it belongs to? Applications use different port numbers. A network application uses a concept called a socket. The exact definition of what a socket is will vary a little, but most agree that it is made up of a local IP address, a local port number, and a protocol. The protocol being either TCP or UDP. As port numbers are unique, so are sockets. Therefore, a socket can identify which application the network data belongs to. That's fairly straightforward so far, but it gets more interesting. A single application, like our web server software over here, can also access the network many times at once. But as this is only one application, it only has one port and one IP. The socket details are the same for all incoming connections. So how can it tell one from the other? It needs to look at the combination of the local socket information and the remote socket information. It can find all of this in the layer 3 and layer 4 headers. It now has 5 pieces of information: the local IP, the local port, the remote IP, the remote port, and the protocol.
Okay, so in TCP, basically you need to know about this different information. Okay, your local one and the remote one. The one is the one you send to, and port number. Okay, your local, where is your sending side and the receiving side, and the protocol you use. Okay, so every TCP communication you need to know about this, because the port was actually say you have one server, right? You have one server and you are receiving data from YouTube. So YouTube may use this port called 34761, right? You may be also on the email, and email may also actually receiving some other data. It may use say 22222 to receive data. So there's some package coming in. You need to know about this package is going to my YouTube, or it should go to my email. Okay. Otherwise you will get confused. Okay. Otherwise you will get confused. So this port number is very important. It determines that there's a incoming package from the internet. The IP address you need to be correct. It's you. You are the receiver, right? You are the receiver. So usually you send your mail to other people. You need to be say number 1 H3, Los Angeles. Okay, something like that. So that's your address. But sometimes people will also write attention, right? College application. So people don't know that, okay, this mail is going to the college admission office. Okay, maybe sometimes you don't write college admission. You write financial aid office, right? So financial aid office. So that mail should go to the financial aid office. So this port number is somewhat a little bit similar to the attention statement in your mail. Okay, if you don't have that port number, you don't know what type of data you are receiving. Okay, so at the same time, your computer may not, and usually it's not, only receiving packages for one reason. Okay, so right now, say I'm playing YouTube, but I may also receiving email. I may also chat into other people in the same computer. So basically, those packages coming from different port, different IP, they will arrive at my computer at the same time. So that remote port number is very important. You do need to have the port number to receive the correct data. And using the port, you collecting the data, you need to reassemble the data back to a file. Okay.
This combination of details is often called the 5-tuple. Each conversation is now truly unique. Let's have a quick look at this on a workstation. I'm using Windows here, but Linux, Mac, and other devices all use the same principles. Here we have a list of processes. Each process has a process ID, shown here in the PID column. These processes all make up applications. Some applications have one process, while others, like Chrome, have several. Some of these processes will be accessing the network. That means they'll have either a TCP or a UDP port assigned. And we can find this from the command line with the command netstat using the ANO flags. A shows all connections, N shows IP addresses instead of host names.
Okay,
and
so using this, you can see IP state, you can see all of the incoming or receiving UDP or TCP protocol. You can see that, okay?
The process ID that owns the connection. Looking at these processes, we can see whether they're using TCP or UDP, the local IP address and port number, the remote IP and port, the state that the connection is in, and the process number, which we can match up on the list we looked at earlier. Now for a quick quiz to see if you're following along. Can you identify which protocols use these headers? What is a socket used for? What pieces of information are in a socket? Detailed answers are available on the website for Patreon supporters, but please feel free to discuss them or ask questions in the comments below. You could also look at online study groups like the Cisco Learning Network for further discussion.
Okay,
And the headers, they're quite different. This is because UDP was assigned to be very lightweight, while TCP was designed with a lot of extra features. For example, TCP is connection-oriented, while UDP is connectionless. Connection-oriented means that TCP will build and track a connection between applications on a pair of hosts before sending data. When they're done, TCP will close this connection. This Stateful connection enables more features, like error recovery and flow control. There's a lot to understand around TCP connections, so we'll use the next video to go into those in detail. UDP, on the other hand, doesn't try to build a connection. It just starts sending data without worrying about any of those details. TCP and UDP also have very different feelings on what to do about errors. UDP, for one, doesn't care about errors. If a packet or segment goes missing, UDP doesn't worry, it just moves on to the next piece of data. TCP, though, does care about lost data. The receiver must acknowledge that all the data that it has received, and if data is lost, TCP will manage the retransmission. Because of this, TCP is known as reliable, while UDP is known as unreliable. This also leads into a TCP feature called windowing. This is where both sides of the conversation agree on how much data can be sent at once before requiring the receiver to acknowledge it. This value is called the window size. If there is no data loss, the window size can dynamically grow. If there is data loss, the window size will dynamically shrink. I'm not going to go into much detail on error recovery and windowing right now, because they've got their own video coming up very soon. The final difference I want to mention at this point is ordered data transfer. TCP uses sequence numbers in the header to track the order that segments should be processed in. This may be critical for some applications, but it does add extra overhead in processing time. This is not important for other applications, which may be why they use UDP.
Okay, so this comparison is very important, okay? Let me explain it, okay? So these two protocols are widely used. One is called TCP, one is called UDP. So UDP is lighter weight, okay? Lighter weight. And TCP is connection oriented. UDP is connectionless. What is connection oriented? Connection oriented means that I am talking to my partner, okay? So I actually would transfer a file using FTP protocol. So I'm going to transmit a big file, and that big file may be a transcript, PDF, okay? So they are ABC score for you, okay? So that file actually need to come and arrive here to be error-free, okay? You cannot allow any error because it's a transcript. You cannot say you lost some data, that is not allowed. So in that situation, you will use TCP, okay? And it is connection oriented. Connection oriented means that the client talking to the server say, is you ready? Okay, and you say ready, I'm going to send data to you. And then you say, okay, I'm ready. And then it start to transmit data one by one. And during this whole process, the transmitter and receiver keep talking to each other. That's called connection oriented. So their connection is actually talking about they are chatting to each other. Okay, they are chatting to each other. While UDP is different. Okay, UDP is not used for file transfer or email. Okay, UDP most of the time used for IP phone. Okay, IP phone or used for video streaming. What that means? It actually connection this, okay? What does it mean by connection this? This one usually used for IP phone, okay? Or used for video streaming, okay? The difference between a connection and the connection is UDP, they do transmit the signal to you, okay? But they don't care about whether you lost it or not. Because, for example, there's a person here, there's another person here, okay? And they are actually talking over the phone, IP phone, okay? So they're talking over the IP phone. So if actually this boy did not hear the girl talking, okay, for 2 seconds, so what? So it doesn't bother, okay? It's okay. We don't care because the girl can ask the boy, hey, I lost your voice. I cannot hear you for a while, okay, and he, the other party would say, okay, I'll say it again, okay. So those kind of applications, such as IP phone or video streaming, it's okay to lose some data, okay. During the transmission, you lost, they can communicate, but they still, it's okay. That's actually use a connection list, okay. But TCP is different. TCP is like you transmit your PDF file for transcript. You transmit some email, containing some certification or something. You cannot afford it to lose it. So you have to use a collection-oriented protocol. So there's an error correction needed. If the data is wrong, you will ask the transmitter to retransmit again, okay? But for some applications such as a phone or video, you lose the data, so what? So you just talk again, right? So you do not need to ask the transmitter to do retransmission, so that people would prefer UDP. So UDP in a way is unreliable protocol, okay? Unreliable but more efficient, okay? So for video streaming purpose, this is better. So for example, like Zoom may be using it, okay? Zoom may be using UDP instead of TCP, okay? And usually more important data, you need to use a TCP to do it. And UDP is more efficient. TCP take more time, more extra scene need to handle, okay? So these are two protocols. We probably stop right here, okay? Here we actually talk about this TCP and UDP, and that's two ways to do transmission, okay? That's two ways to do transmission. Okay, that's about it. Okay, that's about it for the TCP and IP. So basically, we briefly go through the different layer. Okay, different layer. So here in the AP exam, we do need to know about the fault tolerant feature. Okay, fault tolerant feature. We talk about three types of fault tolerant. Number one is hardware fault tolerant. You go through different route. Okay. Number two is software fault tolerant. You do retransmission. Number three is information fault tolerant. You actually add extra error correction code to correct it. Okay. So first one is router and redundancy. There's a network redundancy. Usually you have multiple backup paths to ensure reliability. Sometimes it's also computer redundancy. Say you are working on a computing system such as a stock market. Okay, in the stock market, you may have trading platform, but if one computer go down, the whole stock market need to keep running. So you may have backup computer to run at the same time. That's also called redundancy. Okay, and you have a router. Router is a computer. Router by itself is a computer. You send the data to a router, and router forward your data to the next point. Okay, so basically you go from San Jose to Newark. It's not only one location. You can go by different route. Okay, you can go by different route. Okay, you can go by different route. Go to it. Okay. So this is called routing. Okay, and then there are several routers in the middle, and some of them go down. You will go bypass it. Okay, you will go bypass it. This is a so-called fault tolerant feature. Okay. Okay, and there are some traffic. So you also have the flow control, traffic control, to make sure that your internet don't jam. If it jam, you may also go by different route. Okay, you also go by different route. Okay, this portion we just go through it. Okay, so it's okay. Okay, and your transmission maybe is broadcast mode. Okay, maybe routing mode, maybe broadcast mode. Broadcast mode means that one point sending the data to everybody. This usually is for alarm or alert messages. So, for example, there's an earthquake or there's a tsunami. You need to inform every iPhone user at certain location. Okay. And recently, people may receive the COVID-19 information. When you are traveling to some airport or somewhere, you will be warned by the information that some people got affected is around in your neighborhood. Okay, in your nearby area. Okay, so the broadcast mode usually broadcasting some warning messages. Okay, and router may have log to keep track of where the routing path is. Okay, so. Your package travel, your package travel in different location through different paths to arrive. Okay, this is okay. So this portion, okay. So different layer, they will add more data to it. Okay, so from your file, go down to socket, go down to TCP, go down to IP, go down to Ethernet. Okay, so it actually add on more different header to it, and eventually that's your data frame to be sent now. Okay. Okay, this portion I think is enough so far up to here. Okay. So 3 ways to do redundancy. Okay. You have rerouting, go through different route, retransmission. Okay, and also put in more data to as information redundancy. Okay, this portion we discussed it. Okay, and your internet video streaming is one way, one important thing to look at. Okay, so you have the video streaming being put into MPEG-4, okay, or MPEG-2, and then streaming to your server. Okay, so basically, you are a client. You log into some web server, and the web server find the data, send back to you. Okay, but when they send back to you, they use a TCP or maybe using UDP, and you need to back up a few minutes in your client Windows. Okay, and then those video being streaming to you while it's downloading while you are playing it. Okay. Okay, this is okay. So packet is a small chunk of information that have been carefully formed from a larger chunk of information. Okay, that's actually called packets. Okay, and then package is actually being cut from big chunk of information from in the TCP level. Okay, and TCP is transmit control protocol. This is one of the 2 important protocol in the transport layer. The other one is called UDP. Okay, and this one provides reliable, ordered, and error-checked delivery of a stream of package to the over the internet. And TCP is tightly linked with IP, so sometimes you do see a TCP IP in writing. Okay. And UTP, on the other hand, is actually unreliable, but it's more efficient. So usually used for phone or video purpose. Okay. Okay, this portion is good. Okay. And here you do have a TCP's control diagram. And when you time out, when you request for retransmit, okay, this is the so-called state diagram. Okay. I think this portion good enough for it here, okay? Okay, this because we are in the review mode, so we don't go into some activity, okay? And TCP has such a header, okay? These are extra information being transmitted in TCP level, okay? Okay, so basically your application may be browser, okay? You talk to the host, say YouTube, to download something, then YouTube would cut the big chunk of data into smaller package at TCP level and determine whether it's using TCP or UDP, depending on the application. Then send down to IP level. IP level determine where should the data go, okay? And then that will send to a certain computer one by one, forwarding the data to you. And then it actually go down to the MAC layer. MAC layer is receiving the data from the IP layer, okay? And it will make sure that board to board, one computer board to the other computer board is being safely transmitted. That's called board-to-board communication. And then you go down to transport layer. Physical layer. Physical layer actually converting the digital 0-1 information to the analog signals and transmit it. Okay. So this one we finished. Okay. Domain name server, we talked about it already. Okay. Domain name system is a translation between URL to the IP address. Okay. It's called domain name service. So we have domain name server. It's used to translate the address from a name to the IP address. And sometimes you also including the port number. Okay, port number means that's the location you receive your data and reassemble the data. This is used in the TCP layer. Okay. Okay, next one is talking about some virus you may have. It's called denial of service attack. Okay, And there's another term called distributed denial of service, okay? Distributed, so DDoS, okay? Distributed denial of service, okay? Attack, and this one is DOS, okay? So these different this attack is targeting at your internet, okay? So so let's look at this attack, okay? Domain name server attack called DDoS, okay? Let's look at a video talking about this so-called DDoS. Okay, I think maybe that's actually in the different chapter. Okay, it's okay. Let's actually look at another one. Let's actually go up to the next level. That's actually in the HTTP and HTML. Okay, so let's actually go up one more level in the layer 7. Okay.
I'm Jasmine Lawrence, and I'm a program manager on the Xbox One engineering team. One of our biggest features is called Xbox Live. It's an online service that connects gamers from all around the world, and we rely on the internet to make that happen. This is no easy task, and there are a lot of things happening behind the scenes. The internet is totally changing how people interact and connect. But how does it work? How do the computers all across the world actually communicate with each other? Let's look at web browsing. First, you open a web browser. It's the app you use to access the web pages. Next, you type in the web address or URL, which stands for Uniform Resource Locator, of the website you want to visit.
Okay, so let me go back a little bit, okay? So right here, you are in the layer 7.
Uniform Resource Locator.
Okay, so here you are in the browser. So browser, this one is called URL, you hit return. This one, you have the domain name. You need to translate it to the so-called IP address, okay? And so that go from level 7, go down to level 4, and then go down to layer 3, okay? So this, when you do that, the browser do that, okay?
Of the website you want to visit, like tumblr.com.
Hi, I'm David Karp, the founder of Tumblr, and we're here today to talk about how those web browsers we use every day actually work. So you've probably wondered what actually happens when you type an address into your web browser and then hit enter. And it really is about as crazy as you can imagine. So in that moment, your computer starts talking to another computer called a server that's usually thousands of miles away. And in milliseconds, your computer asks that server for a website, and that server starts to talk back to your computer in a language called HTTP. And HTTP stands for Hypertext Transfer Protocol. And you can kind of think of it as the language that one computer uses to ask another computer for a document. And it's actually really pretty straightforward. If you were to intercept the conversation between your computer and a web server on the internet, it's mainly made up of something called GET requests. And those are really very simply the word GET and then the name of the document that you're requesting. So if you're trying to log into Tumblr and load our login page, all you're doing is sending a GET request to Tumblr's server that says get/login. And that tells Tumblr server that you want all of the HTML code for the Tumblr login page. So HTML stands for Hypertext Markup Language. And you can think of that as the language that you use to tell a web browser how to make a page look.
Okay, so HTTP and HTML are totally two different things, okay? HTTP is a protocol for the browser, okay, that handle the getting information or sending information, okay? HTML is the document type, it's a language, okay? It's actually usually combined with CSS and JavaScript, okay? So it's actually a language, so it's actually a format of a certain file, okay? So these two are totally two different things. And HTTP usually is using HTML to download or send in the data. So sometimes you get confused by these two, but they are totally two different things. HTTP is a layer 7 protocol, while HTML is a file format. Okay, these two are totally two different things.
So if you think about something like Wikipedia, which is really just a big, simple document, and HTML is the language that you use to make that title big and bold, to make the font the right font, to link certain text to certain other pages, to make some text bold, to make some text italic, to put an image in the middle of the page, to align the image to the right, to align the image to the left.
The text of a web page is included directly in the HTML, but other parts, images or videos, are separate files with their own URLs that need to be requested. The browser sends separate HTTP requests for each of these and displays them as they arrive. If a web page has a lot of different images, each of them causes a separate HTTP request, and the page loads slower. Now, sometimes when you browse the web, you're not just requesting pages with GET requests. Sometimes you send information, like when you fill out a form or type a search query. Your browser sends this information in plain text to the web server using an HTTP post request.
So let's say you log into Tumblr. Well, the first thing you do is you make a post request. That is a post to Tumblr's login page that has some data attached to it. It has your email address. It has your password. That goes to Tumblr's server. Tumblr's server figures out that, okay, you're David. It sends a web page back to your browser that says, success, logged in as David. But along with that web page, it also attaches a little bit of invisible cookie data that your browser sees and knows to save. And that's really important because it's really the only way that a website can remember who you are. And all that cookie data really is an ID card for Tumblr. It's a number that identifies you.
Okay, so right here, there's a cookie, there's a post, there's a GET, okay? These three terms, let me explain it. Okay, let me explain it. So number one, these are different methods for the HTTP, okay? So say you are a client, you have your browser, you are a client. You are actually trying to ask for Google. Google is a server, okay? Google is server, so Google. So say you are trying to download a image called a.jpg, okay? So you make request. In that request, you send out get message, using get message to get it. So actually, Google see the get a.jpg request. You send back the file to you. This is called a get message. Okay, this is simple get message. And now the next one is called post message. Post message is different. Post message is your Google or some company, they may give you a form, and then there's a user ID, there's a password, there is some birthday information, and hit submit, okay, something like that. So basically, this kind of information is called post. So the client see that which pages and figure out the information, right? And the data being transmitted from here to here using the post method. So the server receive the data, taking out the data, so the ID being taken out, the name being taken out, the password being taken out. You need to do verification, okay? When you do verification, you need to check the database. Maybe it actually need to connect it with the Citibank's website and get the credit card verification and then send back with it. And then it wait for the determination from Citibank and it's authorized to do something. So those kind of authorization is actually called cookie, okay? It's ID certificate that allow you to do something. So they go back and forth, back and forth, back and forth, and then at the end, your transaction complete, send back your client, okay? So sometimes it's actually like you buy some product from Amazon. So you type in your information for credit card and they do verification and they go back and forth for several transactions until it's done, okay? So that kind of transaction, we call it post, okay? So in the post, you also need to wait for the cookies and whatever digital certificate to make sure that you are verified, okay? You are verified.
You as David, and your web browser holds on to that number And then the next time you refresh Tumblr, the next time you go to tumblr.com, your web browser knows to automatically attach that ID number with the request that it sends over to Tumblr server. So now Tumblr server sees the request coming from your browser, sees the ID number, and knows, okay, this is a request from David.
Now, the internet is completely open. All of its connections are shared, and information is sent in plain text. This makes it possible for hackers to snoop on any personal information that you send over the internet. But safe websites prevent this by asking your web browser to communicate on a secure channel using something called Secure Sockets Layer and its successor, Transport Layer Security. You can think of SSL.
Okay, these two, SSL and TSL, these two are in layer 5, okay? So when they send out the transmission, they need to verify your ID, verify your cookie, verify a lot of things. These are in layer 5. It's actually in the session control, okay, in the session control. So these are the security checking, okay.
And TLS as a layer of security wrapped around your communications to protect them from snooping or tampering. SSL and TLS are active when you see the little lock that appears in your browser address bar next to the H.
Okay, so you see there's a lock. Sometimes you do see HTTP. S means secure, okay? S means secure. So it's different protocol from HTTP, okay? It's a secure version.
HTTPS. The HTTPS protocols ensure that your HTTP requests are secure and protected. When a website asks your browser to engage in a secure connection, it first provides a digital certificate, which is like an official ID card, proving that it's the website it claims to be. Digital certificates are published by certificate authorities, which are trusted entities that verify the identities of websites and issue certificates for them, just like a government can issue IDs or passports.
Okay, so this certificate authority is a third party, okay? It's not even you or Google. It's actually someone in the middle to prove that your certificate is authentic and then allow the transmission to go in, okay? So there's a third party trying to help you to verify your authenticity, okay? So that's actually a different agent. But it is also done in layer 6 or layer 5, okay?
Now, if a website tries to start a secure connection without a properly issued digital certificate, your browser will warn you. That's the basics of web browsing, the part of the internet we see day to day. To summarize, HTTP and DNS manage the sending and receiving of HTML, media files, or anything on the web. What makes this possible under the hood are TCP/IP and router networks that break down and transport information in small packets. Those packets themselves are made up of binary, sequences of ones and zeros that are physically sent through electric wires, fiber optic cables, and wireless network.
Okay, so 7-layer architecture, we talk about the first one, HTTP and domain server. This is layer 6, 7, 6, and 5, okay? TCP is layer 4, okay, this one here, and IP is layer 3 for networking, okay, and you go down to your MAC address and Wi-Fi, that's actually layer 2 and 1, okay. So basically, these are the 3 different important topics in internet, and we use this this one session about 2 hours, and last week to talk about this 7-layer architecture, okay? So the internet testing on the AP ComSci principle pretty much including these different topics, okay?
Fortunately, once you've learned how one layer of the internet works, you can rely on it without remembering all the details. And we can trust that all those layers will work together to successfully deliver information at scale and with reliability.
This one, we finished this lecture, okay? We finished this lecture. So there are some more detail. If you are interested, you're welcome to look at the video, okay? You have this Moodle account. There's several different video you can look at, okay, to study. But anyway, that's right now is 10:49, okay? So let's come back 10:57, okay? 10:57 a.m. We will start to look at the review of the problem, okay? So great. Hello, hear me?
Yes.
Yeah, please turn on your camera, okay? So we'll start to do review problem. So far this whole thing, we look over the 7-layer architecture, okay? Last week, we go through a few problems in the balance set. So today we are going to continue, okay? Any questions so far regarding the internet, this internet topic we covered today? Any questions so far? No question? Okay, if you have question, you can ask, okay? I can explain it one more time for the topic that you don't know, okay? So anyway, I do not hear any request for the question.
Oh, I have a question.
Yes, go ahead.
I'm still having trouble on finding out what the definition of the internet is.
Internet is a network between network. So first thing you need to know about network, okay? Network is very simple. You have two computers, you talk to each other, it's called network. Right? Is that okay?
And the internet is
internet is okay. So now two computers can form a network. So maybe there's a building, right? So say that's assume this building is owned by IBM. Inside IBM, there may be 100 computers. So the 100 computers connecting to each other, no matter it's using wire or you're using Wi-Fi, it forms a network, right? Is that okay?
Yeah.
So the so-called internet is, how about us actually connecting all of the computer together worldwide? So that's a network between network. So this the IBM may go to a certain gateway, okay, certain gateway, and then go on to the internet, okay. So for example, your local, you will go through a ISP, okay. So your AT&T or your Comcast. So since there they connected to the whole network, okay, on the Earth. And then you go into local again if they using a router in a certain person's computer. So the blue one, we call it the internet. Okay, this one is not. Your local is red one. Up to the ISP is your local area network. It's LAN. Is that okay?
Yeah. So basically,
blue one is the internet. Blue one is the backbone that connecting everybody on Earth together.
So it's the internet is basically all networks like connected together, right?
Yeah.
Okay, got it. Thank you.
It's a network between network. Yeah. Any more question? It's good to ask question.
And also, like, what is an IP address like necessarily? So the IP address is basically like the numbers that every device has to communicate, right?
Yeah, IP address is like, okay, think about computer. Computer just use binary data, right?
Mm-hmm.
So actually, it's impossible that you actually try to find a computer using google.com.
Mm-hmm.
It will never be that way, right? Because this is actually a string. So that's not how we will do. How we will actually have, say, 240.51.25.2.7. So it's use 4 bytes as the address attaching to that domain name.
Mm-hmm.
So here there's a server calling this IP address. And then you have another computer that has another IP address, right? So you need to transmit data from here to here. To make sure that the destination will receive the right data, you need to tell people who is the sender, who is the receiver. So sender, receiver actually will be represented by the IP addresses.
Wait, so the IP address is the number to what again?
The computer. IP address is the address to the computer. So google.com actually eventually is one IP address. So I'm going to ask that IP address to give me some data. So Google will send me one file and it will send a file to me and indicating that this is from 251.25.2.7. It sent me a data and that is my, say, college transcript, something like that. So in the people's war, we know that it's yahoo.com, it's actually tumblr.com, it's google.com. In the hardware side, they only know this is 251.25.2.7, send some data to you. Is that okay?
Wait, so I thought you were saying that the IP address was the number to the google.com stuff.
Yeah, that's actually, yeah, it's actually that, yeah.
But
and there's a translation scheme called DNS, domain name server. They translate the name to IP address. So eventually, when you send out a datagram or your package, it actually has a header carrying the IP address.
Okay, that makes sense. I get it. Thank you.
In the middle of the class, we actually cover the TCP and also UDP. They do have the IP and port number. Remember that? In their datagram, they do carry that. Is that okay?
Yeah, I get it. All right.
So basically, okay, let's do it this way. My name is so-called Eric, right? So my name is this. But to reach me, you don't call phone number by this. You call my phone number of this. Is that okay? So this is some sort of like IP address. Is that okay? You call me, really call my phone number. You don't call my name, right?
Mm-hmm.
Use your iPhone.
Mm-hmm.
So the browser's purpose is that you got the colleague's name that I'm trying to get the data from google.com, but it really is translated to this 251.25.2.7. That is the machine, the IP address for that machine that I'm going to request the data for. Is that okay? The by hardware is something like that, okay? Okay, any more question?
No, it's fine. I get it.
Other people, any question? Okay, Emma, are you okay?
Yeah, I'm okay.
Okay, so last week we reviewed about 7 problems. So today I'm going to repeat it because I'm not sure whether I cover every problem or not, but I don't need students. So the first 7 problems, I will just go over it by myself one more time, okay? Be quickly, okay? So number 1, which of the following is true about the package, okay? So package arrive and receive computer in the same order. No, it's not in the same order. So 1 is wrong, A is wrong. Package arrive and receiving computer in different order sent by the computer. Yes, it actually in different order. So B is correct. C, when sent by computer, package guaranteed to arrive and no, it doesn't guarantee arrival. One sending file will be contain one package. No, it will be breaking down in several chunks of the data. Okay, so 1 is B. 2, which characteristic of the internet protocol help fuel pay the rapid growth of the internet. So it's a scalable. Okay, it's open and scalable. So basically, this one is open. Actually, is also designed to be growing scalable. So B and C. Okay. Next one, actually, which of the following protocol define how computers send package of data to each other. This one actually it had TCP, but I told people last week that actually both TCP and UDP should be. Both of them are in the so-called transport layer. So this one, Baron has a technical error. Okay, this one, Baron has a technical error. If he try to avoid that, he should not put one of them in here, okay? Number 4, which are the protocol responsible for address and routing your computer that actually is IP address, okay? Next one, when is it advantageous using UDP? Okay, UDP we talk about is unreliable, but it is more faster, okay? And actually UDP actually when speed of transfer is more important than the error, so it's D, okay? Usually for IP phone and video, you can afford the loss of the quality, okay? So number 6, which type of computer device is made by many type of company? Okay, it's basically by open standard and protocol, so people can actually share the same protocol, okay? Number 7, why are most websites designed to work within a boundary of current web protocol? Why they don't actually use something else, okay? Number 1, it's not illegal, so B is gone, okay? Not because it's illegal, okay? 2, actually B, okay? B is gone. C, current protocol are the limit of the, okay? Actually, no, it's not a limit. D, okay, if protocol is executed, is seated, okay? ISP assume a website with broken, okay? No, it's not, okay? So number 7 is A, okay? Number 8, let me have, okay, Alex, you go first, okay, number 8. What's the purpose of transition from IPv4 to IPv6? IPv4 to IPv6. Alex, you hear me?
Yeah.
Yes.
I think it's probably B.
You don't have the enough space, okay? So how many bits for IPv4? Address space. And how many bits for IPv6? In the video, actually, we
I
do
don't
see.
remember the exact number.
Okay, you need to pay attention. Okay, this is very basic portion. Okay. How about Taolu? Do you remember this? Taolu, you.
Oh, for number 8.
I'm talking about how many bits or how many bytes is used for IPv4.
I'm not sure.
Okay, this is very basic. Okay, this is very basic. This is probably cannot be even more basic. Okay, you guys have to learn it. Okay, otherwise, this question actually just telling me you are not watching this whole session. Okay, this is actually very basic. How about canceling? How many bytes for IPv4? Or how many bits?
4?
Yes, 4 bytes. Okay, 4 bytes. Okay, if you cannot answer this question, means that you actually do not watch the video, or you do not have any background knowledge at all. Okay, that's not good. That's actually not good. How about Nathan? How many bytes for IPv6?
16.
No. How about Nico? Nico, wait, do you remember? How many bytes or how many bits for it?
128.
Yes. Okay. So you see, 2 girls are remembering. I think boys has a problem of just maybe playing video game or something. Okay. I don't know what you are doing, but look like girls are more attentive in the classes. Okay. That's a typical problem. Okay. Pay more attention. Okay. That's what I can say. I'm not trying to find trouble with you, but that's what I can tell you. Must work harder. Okay. Okay, so IPv4 is a 4 bytes, okay? Usually it's 125.4.7.1. So we have been talking about this the whole day, and you don't know how many bytes it is. That means that you pay no attention to the class, okay? Really apparently. IPv6, if you don't remember, I can actually forgive you, okay? Because It's just show up once or twice. This one actually is 7 by 128, okay? And some question may ask you how much address space being added. So it actually being added by totally 3 byte, okay? 3 byte is A times 3, okay? So actually 24 bit create 2 raised to the power 24 times more address spaces, okay? A lot of them. Okay, the purpose of doing this is like, okay, the IPv4 is found to be too small. Okay, so B, okay, B. Okay. Okay, next one, let me have second problem, number 9. Let me have Emma. Okay, Emma, how about number 9?
C.
Okay, C, actually number 9, redundancy. We have 3 kinds of redundancy, right? We talk about it in the class. So Emma, do you still remember what are the 3 types of redundancy?
Hardware redundancy, software redundancy, and information.
Okay, good. Okay, very good. So you see, I say girls always be more attentive in classes. Okay, I don't know why, but this actually is the trend. So hardware redundancy is actually you providing multiple computer or multiple paths. So when one computer fail or one path fail, you can go by a different one. Okay, that's actually hardware redundancy. Software redundancy means that you send some data, it failed, you did not receive the package, so you request the sender to transmit it. That's called software redundancy. Third one is information. Information means that you add more data field to it, so you include more data to the frame. Okay, so basically redundancy here is talking about hardware redundancy. So redundancy makes the connection more reliable. Okay, so you see. Okay, number 10, Zhang. Okay, Zhang, this one. Okay, how to completely isolate A? How many cut need to be? Like Zhang Liu.
3, B.
How to look at it?
The lines that need to be cut. And that's 3 lines, right?
Where?
AC, AB, and AD.
Mm-hmm.
Yeah, so that's 3 lines.
You need to cut over here.
Yeah.
So can we do this?
No.
No, okay. So basically you want to isolate this one is here. How about this one? If I want to isolate F, how many?
F, 4.
1, 2, 3, 4, 5. 5.
I mean 5. My bad. Sorry.
Okay. Okay. Can we do fewer to isolate it? No, you cannot. Here already 5 of them. Okay. Okay, next one, canceling. Okay, canceling. Yeah, this one actually is F. Okay, we already showed actually 5. Okay. This one actually, let me see, canceling. Okay, number 12. How many lines needed to cut A completely? Hello, canceling D. Okay.
4.
Why 4?
Wait, what's the thing in the middle for though?
It's actually a server in the middle.
Huh.
The answer is 1. You just cut this line, you see.
Oh, okay.
So this one, okay. So what's the difference of this chart like this network and this network? What's the difference between these two networks? When people draw in this way and this way, what's the difference between the network, this one actually is not what they ask, okay? But when you see a picture like this and this, what's the difference? What's the difference of these two networks? Occasionally, do you know?
There's a circle in the middle.
And what does that circle mean?
I don't know.
Okay, whoever know.
Does it mean it's like centralized?
Yes, this is a centralized computer. This is distributed system. Is okay? So this one centralized means that if the center break, everybody are done. No communication anymore. Is okay?
Yeah.
Is okay? Nowadays, people prefer the so-called distributed system because if this bridge is down, we still can communicate. If F is down, we still can communicate. That's distributed system, okay? So that actually one line needed to break it down, okay? So number 13, let me have Malcolm, okay? Malcolm, what is the answer for number 13?
Is it 1?
Minimum number of the computer must go through when traveling from B to D, okay? B to D, you actually, this kind of problem, you look at the shortest path. Is that okay? Shortest path, yes, so it's 1, okay? It's 1. So how about this same problem, okay? How about B to E?
Is it 2? Or no, it's still 1.
Still 1, okay, still 1. This is the shortest path problem, but sometimes they also have the minimum spanning tree problem, okay? Minimum spanning tree problem is like, okay, how many lines needed to connect the whole network? So basically the minimum spanning tree is that you connect A to B, okay? Because it is the minimum number of things you need to have, okay? Next one, you try to connect one more node to the network, okay? So usually you go either E or D or C, okay? That's the reason that you pick E, okay? And next one, you actually try to add another one. So you actually may pick C, okay? And the next one, you can pick D or F, okay? So you can pick one of them. But basically, you can build up something that is, this is called minimum spanning tree, okay? So these are some algorithms in computer science, okay? But we don't test it, okay? We don't test it, but sometimes some courses may teach it, okay? Number 14, let me have Michael, okay? Michael Wen. This one, number 14. There's a line in B and C fail, okay? So which computer must go through between B and C?
A.
A is a must, okay? This one is pretty simple. Number 15, let me have, okay? Let me have Nathan Chen, okay? The internet is built on open standard, okay? In this context, what does open really mean?
Is it A?
Freely and can be used by anyone. Yes, it actually can be used freely and can be by anyone, okay? B, the standard cannot be used for proprietary, okay, no. C, the standard can be used in any program in inclusive access to the web, okay? Inclusive access means that it can use, no. The official standard can be made and updated by anyone, no. Usually, who edit it? I mean, who can edit it? Mason, who can edit it?
Everyone, the public.
No. You make proposal and the so-called internet engineering task force will edit it, okay? We may talk about it already, but just remind you, okay? Next week we'll talk about it one more time, okay? So no problem. Next one, we have Nathan Ye, okay? Number 16.
Is it B?
B? Okay, which of the following best describe fault-tolerant nature of the internet? Okay. Okay, it's actually when the internet fail, the package choose different paths. Yes, it's actually B is true for sure. Okay, let's check the other one because there is all of above solution as well. Pick the fastest route? No, sometimes no, and usually no. Okay, so A is wrong. So you can safely pick B. Is okay?
Yeah.
Okay. Number 17. Okay, number 17. Nico Wei. Okay, which of the following statement about package are true? Pick two answer.
Is it B and C?
B and C?
B and C.
Okay, B and C. Okay, let's see. Okay, package must be received in order. That's wrong, right? They will reorder it. Package does not have the to receive in the order they are sent. Yes. Package can travel different paths. Yes. Package choose the fastest path. No. Okay, so basically B and C. Okay, number 18. Okay, number 18. Let me have Sunny, number 18. Okay, so is one true or wrong? Redundancy show the package traveling slow down. Will that slow down or no?
Is it C?
Redundancy will slow down the package travel from sending computer to receiving computer. Okay. Second, redundancy allow 18 more devices without disrupting. So B2 is correct. Redundancy make the internet fault tolerant. Okay. So now the question down to C or D, right? So is one redundancy will slow down or not? Actually, the parents say is C, okay, but this one I would say arguable. Why I say arguable? Redundancy slow down. You having the redundancy may not slow down. Why is that? Because your path, nobody say that the path you are using is faster. You know what I'm saying? You go to the internet, you just pick some route. And whether you bypass someone is slowing down or making it faster, we actually don't know. Okay, so but because the book say C, I would say B, but usually I don't say this one no problem would be there because it's very arguable. Okay, very arguable. Redundancy just means that you provide more paths. You provide more paths and you slow down. Maybe not, right? Maybe not. Is okay? You slow down because you raise a breakdown, but it doesn't mean that you have a redundancy. The whole system will slow down. By adding one more computer or router into the internet, will that slow down the system? No. The answer is no. It never slow down your computer. Is that okay? But if your network or computer fail, it slow down. Yes, that will slow down. Does that make sense?
Yeah.
Okay. So this one, but it's arguable. I would say arguable. And I cannot say it's totally wrong as well. Okay. I cannot say it's totally wrong as well. Number 19, Tao Lu, okay. What's the benefit of the internet standard?
Is it C?
So one is true or wrong. Internet procedure ensures software or hardware created by different company communicating each other. Is that true or wrong?
It's wrong.
This one actually is true, right? You have the open standard is true, right?
Oh, okay. Yeah.
You pick B and then you say this one's wrong. It's very strange.
No, I said C.
C? Okay.
Yeah, I said C at first.
Yeah, okay. Anyway, this one is true. Okay, so this is true. So second one, internet standard written to ensure internet protocol are open and free. This one is true, right? This is true. This one very simple. How about the third one? Internet standard reduce the risk of the virus, whatever malicious software. No, the standard doesn't ensure that.
Okay.
Right? Standard never remove the virus. How can you remove the virus by setting standard? The hacker don't actually follow standard. Okay, is that okay?
Yep.
The hacker never follows standard. Number 20. Okay, number 20. Let me go back to Alex. Okay, Alex John, number 20.
D.
Everything. Okay, sender IP addresses actually receivers ID address and also data. Okay, number 21. Emma, please.
120?
21.
Oh, yeah, 120.
100. You say D. Okay.
Yeah.
Okay, good. So here, this one actually, what's the performance wrong in series? In series is just summing up. Okay, so it's D. Yes. Number 22. Let me have Jiang. Okay. So this one has two identical processors can run in parallel. Okay. What is the best approximate minimum possible time? Okay, it's run in parallel. Okay, each processor can only run one process at a time. Each process can be executed in a single processor, so you cannot break down into two halves. Okay, so the table showing this. Okay, assuming that none of the processes are depending on the other. So what is the minimum amount of time you need to run these three tasks? Jiang Liu. Okay, Jiang. Jiang, hear me? Hello? Jiang, hear me?
Wait, you're talking to me?
Yeah, I'm talking to you. Yes.
Okay, my bad.
22.
B, A.
How to solve this one?
Wait, it says minimum, so
minimum, yeah. How to solve this one? Yeah.
The minimum is just the least.
The least.
Yeah.
There are two processes. How to solve this problem?
I don't really remember.
You don't really remember? That's okay. Let me ask another person. Okay. How about Kathleen? Kathleen, how to solve this problem? You have three processes. You put into two processing unit. Two processors. How to solve the minimum time that you need it? Kathleen, hear me?
Can you go over it?
So this problem 22.
Yeah.
You have two processors run in parallel. So you have three tasks to be finished. The time are these if you run them separately. So now you put into the two processors, and how is the minimum time you need to finish all the three? Okay. So who knows it? Who knows it? Say your name and you can talk about it. Who knows how to solve this problem?
This is Alex. Is it 70 seconds B?
And how to solve it?
Because you have like two processors, so like
yes.
for one of them, you put like process 3, and that takes 50 seconds, and for the other one, you put process 2, that takes 40 seconds. So after the process 2 finishes running, you put process 1 into that one, and then that takes like the total 70
So the
seconds.
minimum will be this, okay? Minimum will be this. So if you say 50 here, 40 here, it will not be minimum. So minimum is you put this one here, okay? So if 3 processor, in case that you have 3 processor, P1, P2, P3, right? Then you have 30, 40, 50. So the minimum time needed will be 40. Is that okay? Is that okay? Hello, is that okay?
Yeah.
Okay, anyway. Number 23, okay? 23 is a little bit more harder, okay? This one, let me see. Malcolm, okay? Can you solve this problem? So here, a computer have 2 identical processors, okay? Each process can run only one process at a time. Each process must be executed in single processor. 1 and 2 must be serial. So 1 and 2 don't work with other people, okay? So 1 and 2 serial, don't work with other people. 3 and 4 and 5 can be parallel. So this one, okay. So how to actually, so what would be the minimum time need to run all the 5 in parallel?
I don't really understand what like 1 and 2 are. What does that mean that they can be run in a series?
It can only be run in series means that you cannot share the time with other people.
Okay.
Yes. When it run, the other CPU must be idle. Nobody can share with it. So in parallel means that you have task A and task B side by side. That's in parallel. Serial means that you have to do it this way. A finish and then do B.
Would it be C 130 seconds?
Okay, how to solve it?
So like on one side you could have process 3 running, and then on the other side you could have 4 and 5 running, which would be 80 seconds. And then you have 1 and 2 run after that.
Or before that, okay? So this 123, we have this. So this is 50 plus 80 is 130, okay? Is that okay? So it deal with the serial portion over here and the parallel portion over here, okay? And serial before or after parallel is the same thing. There's no difference, okay? So this
Wait,
was,
I have a question.
Yes, go ahead.
Can't you make it in 90 seconds?
How to make it?
So you run 1 and 2 on one processor, and then you run 3?
No, it said that the 1 and 2 must be in series.
Yeah, but like they run in series on the same processor. So you first run.
They don't share, they don't allow the other processor to be used. When they say it's a series, means that they don't allow other process to. So it's not possible that task 1 sharing with task 3 running at the same time.
Wait, why can't you just have 1 and 2 run on one processor and then?
No, that's not. When you say in series, means that they don't allow people to run side by side with them.
Oh, okay.
This happened when what? Okay, let me explain it. This happened when actually say number 1, okay, actually a number 2, they get input from outside, for example, right? And then 3 and 4 and 5 need to wait for their input. So there's no way that your 3 can run with it, right? Is that okay?
Yeah, okay.
Okay. Say this is input only 1 keyboard. So actually 1 and 2 also need to be in series. You type in some data and the other one type in some data. So you have either do 1, 2 or 2, 1, okay? But there's no way that you do 1 and 2 side by side. Or you do 1 and then put 3 on each side. No, that's sorry. something you cannot parallelize. So something you cannot parallelize, we call it in series, okay? So essentially, this one is a good question, okay? That's a good question that how to, why you need to run them in series or in parallel, okay? This question is a good question, okay, good. Number 24, okay, number 24, let me have Michael Wade, okay, Michael 24.
Is it B?
Independent broken down into independent operation. Okay, so 24, that's actually a parallelable part, okay? So you need to study your data to be parallelable. So what is parallelable? Let me show you some information, okay? So you have, say you have A equals B plus C, okay? And then D equals E plus F, okay? And these two actually parallelable. Why? Because this statement number 1 and number 2, they don't depend on each other. Is that okay? Nobody depend on each other. This one is called parallelable instruction. Okay, instruction 1 and instruction 2 are parallelable instruction. So sometimes it's not something like this. Sometimes it actually is B plus C equals A, and then A plus D equals F. In this case, instruction 2 is waiting for instruction 1 to finish. So you must go instruction 1 and instruction 2, okay? This one called input dependency. Is that okay? This one called input dependency. Input dependency means that your data need to be ready before the next one it can be used. That's called input dependency. There is another kind of dependency called output dependency. Say you have A plus B equals C, okay? A equals D plus E. Okay, this one input, this one output, right? But these two also cannot run together, okay? Even though this second instruction does not export data from the first one, you do not need the result. But the problem is, since you are updating A, so this one may finish before instruction 1 go first. So if you do side by side, for example, then you may update A before it being read by instruction 1. So that will create trouble. This one called output dependency. So whether you have the input dependency or output dependency, these are something that you cannot parallelize. Does that make sense? Hello, does that make sense? Any question? No question? These are two examples of what are the dependency that may cause it, okay? Okay, 25, let me see. Let me have Nathan Chen, okay, 25. Nathan, 25.
Would it be B?
Mm-hmm. So a program check picture in 1,000 seconds to check 100, right? So the speed right now is actually right now is actually 1,000 for 100 pictures. So actually 10 seconds per picture. Okay, that's the efficiency you have. So the other one actually 2 programs take 10 seconds to check 100. So basically it actually is 10 seconds divided by 100 pictures. So actually is 0.1 second per picture. So the improvement from here to here is 100 times improvement. 25. Is that okay?
Yeah.
Okay. 26. Okay, 26. Let me have Nathan. Yeah. Okay. Nathan. Another Nathan.
On A.
Okay. This one, the program take 40 seconds to solve 300 students based on GPA. Okay, the same program in parallel. Two programs still takes 40 seconds. That means there's no improvement, right? No improvement means your speed up is 1, same time, okay? 27, let me have Nico Wei, okay?
Is it B?
Okay, how to solve it, okay? The program takes 3 seconds to set up and run the processor in parallel, okay? And then how serial parallel would take if these are to be processed, okay? So 2 10 megapixel image, 1 15 megapixel image, and 1 20 megapixel image to be processed, okay? Takes 3 seconds to set up and can run 4 processors in parallel, okay? 4 processors in parallel. So what's your answer?
Just B, but I don't know.
How to solve this one?
Like, can you go over it since I'm not sure?
It's actually serial and parallel. So there are 4 processes. So how are you going to load it to maximize the efficiency? You have 4 files. It's a 10 pixel, 2 10 megapixel, 1 15 megapixel, and 1 20 megapixel. So basically, that's a call. It's an A-type file, B-type file, C-type file, right? So for processor, the best solution should be running A, B, C in parallel, right? Is that okay?
Uh-huh.
And then there's a 3-second setup time. So set up 3 seconds, and maximum here actually is 8 seconds. So the solution is 11 seconds, and then no solution is this one, okay?
Okay.
This one, no solution. All of the solution described over here is wrong, okay? Is that okay?
Mm-hmm.
I think if you have the book and you check the answer, it say is what? It actually is D, okay, 20 seconds. That's because that here, I think it tried to say 2 process, but it actually put a 4. That's wrong. Does that make sense?
Yeah.
So that's this one has a technical error. This one actually no solution. X, okay. When it's only 2 processors, then the solution that it provides by itself is correct. But it's a technical error by Barrett, okay. 29, we have Semi, okay, Semi, yeah.
A.
Okay, this one. How distributed can be help execute the program, okay? To predict the path of a hurricane. So hurricane goes through, okay? Extremely large data set, okay? This problem is so large, complicated, okay, to solve in single project. So basically, you need to use a distributed computer. So you want it to run it in parallel, okay? So B is wrong because in series is wrong, okay? C, distributed computer can speed up time by using multiple processors Actually, this one compared with A is distributed the same. Here, single computer, that's wrong. Okay, distributed computing is in multiple locations, so it's wrong because there's no single computer. D is also wrong. Okay, so it's A. Okay, number 29. Let me have. Wait, go away already. Okay, next one. Go back to Alex. Okay, number 29.
Sped up D 2 times.
So program take 10 seconds to show 300 students data. Okay, when the program run in 2 computers in parallel, it takes only 5 seconds to run it. So speed up is 2 times. Yes, 29 is D 2 times. Okay. Okay, so we finished this balance set. Okay, and we still have some time. Okay, we still have about 12 minutes of time. Okay, so here we cannot start a new chapter, but what I will do is, okay, you have a project you need to be done, okay? That actually is called digital portfolio. And the digital portfolio, you need to record for 1 minute of the video, okay? So 1 minute of the video, you need to finish, okay? You need to do the video. Okay, let's talk about the video recording, okay? So number one, you need to know about what you want to actually show in your video, okay? You actually need to know what you really want to show in your video, okay? So that's the reason that we have some project over here, okay? Some project over here. Okay, some project right here, okay? And we would like to show the roll die and it work, okay? So something like that. We actually have such a program. We would like to show it, okay? So what happened is like, when you design your 1 minute program, okay? When you design the one program, number one, you need to some video that you do screen shot, okay? Screenshot. So you may need to have certain, say, you may need to have, like me, I have the so-called Camtasia, okay? Camtasia that I can do recording, okay? And you can also use Zoom to actually record it as well. So another way to actually do recording, you can have the room and you do using Room to record. I think this one is free, okay? So you just actually go to Room, okay? And you take the video and download to your local, okay? So with video on, no, video off is okay. You just know how to share your screen and you download it. So these are the free video recording tool you can have. And you can also download the so-called Microsoft recorder, okay? Microsoft recorder, Microsoft expression recorder, okay? So you can type the so-called Microsoft, okay? Expression free recorder, okay? This one you should be able to download the Microsoft encoder for, okay? That actually you can download and do recording and do editing as well. There are some other tools like, there's some free tool used by screen capture, okay? So free screen capture tool, okay? Screen capture tool, you can actually look at it, okay? So there are some free screen capture tool you can actually find, okay? Then you need that, okay? That's one thing you need to do. Number one is actually find a video capturing tool. Second is that before you do it, you need to plan your scenario. So you need to plan your scenario. So you have 1 minute to go, okay? You must remember that what you need to actually demonstrate, okay? So for example, I want to demonstrate the so-called roll die, okay? So you should play a few seconds, okay, showing that, okay, initially your screen is empty, right? and then you need to do, say, provide a certain typing or something here. So here, click here to roll die. Okay, this program is very simple. You need to write some. So you take the video of these, but you would like to add some label to it. Okay, and then to show people. But you cannot say it. You cannot record in the audio because they don't want you to have your sound, because sound can identify which person is talking. So the reader may know who you are. That actually is not legal. Okay, that's not legal. So you need to have the caption, okay, and describing it, and then you click, okay, and you roll. Roll, you need to write something, okay, what happened here, okay, whatever, and then you roll again, what happened here, okay, and something like that. But you need to put down into there in your scenario. So this program is pretty simple. So basically, it's a little bit too simple, and basically this one is too simple to demonstrate. Okay, let me try to find some more difficult one. So say this one, tic-tac-toe game. Okay, this tic-tac-toe game. So this tic-tac-toe game, you need to explain what's going on. Okay, so check. Actually, let's do this one. Okay, so let's do it. Okay, this one is not running. Okay, let me see. Okay, so you need to, while you're playing, you need to explain what's going on. Okay, so this one, okay, you have win, game over. This is one way you do it, and you need to plan it. So you do it again, and so you have 1 minute to go, right? But the way before you actually recording the video, you must know, okay, how many seconds. Okay, so actually second 1 to actually 20. What should you do here? Okay, write it down. Okay. And then actually second, actually 21 to actually 30, what are you going to do? Okay, so plan your scenario. So make sure that all the function you want to demonstrate actually is there. Okay, actually is there. And then you take some video to do it. Okay, but if the time is too short or something, you may go back to adjust your scenario or take out some item that's actually taking too long. Okay. Okay, taking too long. So basically, you must demonstrate the feature that you want to demonstrate for your software or whatever app you have. Okay, and then when you go to your say your video editing. So for me, I'm using this Camtasia. Okay, I use this one every day. Okay, every day. So whenever I talk about it, I actually do backend process. Whenever we finish a lecture, I process it before I post to the internet. So I cut the personal information in the front or in the end when we do some discussion. Usually those are garbage, okay? So I cut it before I post it, okay? So then every second counts, okay? So you have 1 minute to do. You must plan that, okay, what should I put over here? What should I put over here, right? You need to plan it and then put a video over there. Some of them may not be video. So you may use your PowerPoint, say right here, I'm going to generate a certain PowerPoint. So I draw it, okay, I draw it in using PowerPoint. Say this chart, I need this one into my video, right? So I save this certain page. After drawing, I save it as a JPEG, okay? And I save it, okay? I save the whole thing in just one page. So I save it, okay? So the page being saved. The page being saved, and then I may have, so let me open some existing project, right? So for example, this one, I have some video I'm editing, okay? So loading it, and then I may include one more image, okay? So sometime here, you see every time actually I do have some video, right? And not image. So here, every time you see, I have such an image, course image. This one actually, I use a PowerPoint to generate, and every time I put it here. So you organize your video and picture and drawing by yourself or picture, and then you try to organize in 1 minute, okay? And make sure that you follow your scenario. But maybe somewhere you need to put some picture to actually help to explain your content, okay? But the rule is that you cannot voice out, okay? And you also need to make sure whether you show the so-called abstraction of the data structure, or you show the picture that you want, you show some feature that you need to show, okay? They are required by the College Board, so make sure that you read the whole thing carefully, okay? Background music, I maybe okay, I don't remember, okay? Maybe okay, then if it's okay, you put your background music. For example, this is my header music, okay? I have been putting this many times, right? This one is my background music. Okay, let me get started, okay? Okay, so here the background music may be allowed. You have to check the rule. If okay, you put some background music, but usually there's a certain file size limit, okay? So don't put too much of them. You may slow down your program, okay? But sometimes if your audio is too big, you can compress it or make it smaller using the Audacity to compress your audio file, okay? So you can also download this tool called Audacity to do audio processing or remove the audio error, okay? So this one is a tool you can download called Audacity, okay? So here I just show you some tool and technique to compile your video. Any question about this part? It's very short. I use 10 minutes to talk about it. Any question about this one? Hello, any question? So remember the due date, okay? Due date for the digital portfolio is May 2nd, okay? It's not the testing day, okay? Testing day, the AP concept principle, I remember maybe nice, okay? You have to check this time. But the due date for the digital portfolio is earlier, okay? It's May 2nd, okay? Any question? Emma, any question?
No.
No question. How about Alice? Are you okay?
Yeah.
Yeah. Who has already submitted a digital portfolio? Any one of you? Hello? Any one of you already submitted a digital portfolio? Any one of you? Okay. I can only help you this much, okay? Let me know if you have some question, okay? If no question, we are done here today, okay? Any question?
Wait, so can you like code about anything you want?
I want for what?
Like for the portfolio.
It's required by the College Board.
Okay. And it doesn't have to be like too complicated, right?
It doesn't have to complicate it, but they have certain rules you need to have, such as you need to demonstrate abstraction of data structure and program structure by abstraction. You need to demonstrate at least one loop.
Okay.
And one function. So there are some rules you need to follow. And usually people like to demonstrate a bigger program because some program too simple, just showing your weakness in programming, right? And another thing is that your project must be authentic. Authentic means that don't copy people's ideas. So the one I show you usually is a bad idea. The one I show you, say, tic-tac-toe game or the die throwing, those kind of things are not welcome usually, because this one is a some program that a lot of people develop in it. So it's not suggested to write such a program, okay? They will even think that you copy from somewhere else. So please try to create new idea. And one of the things that test their grading criteria is the creativity. So they do have such a criteria, okay? And it's not grading by me, it's grading by the College Board. They will have reader just like your normal AP reader for the ASIC. And this digital portfolio takes 30% of your overall AP, okay? Is that okay? It's
Yeah.
taking 80%. So here you have the maybe AP pass score, okay? Actually, there's a website called AP Test Score, AP Pass, okay, this one. Okay, so you can come to this website and then there are certain calculators. So basically, for example, let's actually pick, let's see, science, AP concept, AP computer science. Wait, this is it, okay. Close it, okay. So this one is AP computer science A's distribution, okay. So you can actually look at, it's based on 2016, 2009, or 2004. So you can play around the numbers, seeing how much you can get what score. Is that okay? But based on the 2016 data assumption, there are certain subject you can play around, okay? This website is called AP Pass. Is that okay? This one is called AP Pass. So here, let me copy this one to the chat box. So if you have time, you want to just play around, you can look at it, okay? This one is a pass score, and you can budget how much you still need to improve for each subject. Any more questions? Any other question? Okay, if no question, that's it for today, okay? Thank you. Thank you. Bye now. Bye-bye.